In our previous discussion on PICs, we mentioned that the PICs can be programmed using microchip assembly language. Programming using an assembly language is a bit difficult. On the other hand, programming using a high-level language is a lot more easier. In this lecture, we are going to show how a high-level language can be used to program PICs. The high-level programming language that has been specifically designed to program PICs is Mikro C. Mikro C programming language is essentially standard C programming language that has been customized to suit the development of PIC programs. It has got the same syntax as the standard C programming language. It also borrows some syntax from the C++ programming language. When a Mikro C program is compiled, it produces a hex file that can be downloaded into a PIC. Variables in Mikro C programming language refer to locations in the PIC data RAM. That is, they refer to the file registers. Remember, the file registers are made up of special function registers, SFRs in short, and general purpose registers, GPRs in short. SFR locations can be accessed using the names of the SFRs as the variables. These names are already defined in the Mikro C programming language as variables. Hence, you do not need to declare these names as variables before using them. GPR locations are accessed through variables that you would have declared as the programmer. The working space can be accessed using the names R0 through to R15. R0 refers to the lowest address in the working space, and R15 refers to the highest address in the working space. Remember, the working space is the last 16 locations in each bank of the data RAM. And remember, the working space is mirrored in all the 4 banks. When we use a microchip assembly language to program a PIC, we need to specifically change banks whenever there is need. However, on the other hand, when we use Mikro C programming language, we do not need to change the banks. The compiler changes the banks for us whenever there is that need. Now let's look at the types of variables that are found in Mikro C programming language. The variables char, short int, and unsigned short int are 8-bit numbers. Therefore, they are stored in a single file register. Remember, the file registers are 8-bit storage locations. The variables int and unsigned int are 16-bit numbers. Therefore, they require 2 file registers. Whenever you declare variables of type int or unsigned int, the compiler automatically assigns the variable to 2 file registers. Operations and assignments of values to variables are done the same way they are done when using the standard C programming language. On the slide, we've got a couple of examples and a couple of illustrations. In the first example, we are assigning the value 58 into the SFR timer 0. In the second example, we are dividing the contents of SFR address L by 4 and assign the results to the variable weight. The variable weight is a variable that would have been declared by the programmer. We also have got some examples of operators that are used when making comparisons, and we have got some examples of statements that are used when deciding between the path a program is taking and when looping in a program. A number of PIC instructions operate on the individual bits in the file registers. There are two ways of addressing the individual bits in a file register when using Mikro C programming language. In the first way, the name of the SFR that contains the bit or the variable name of the GPR that contains the bit together with the name of the bit or the bit position separated by a dot are used to address the bit. For example, if you want to address the global interrupt enable bit, which is found in the indcon register, we address it as indcon.gie. If you want to address bit 7 in the PIR1 SFR, we address it as PIR1.B7. B0 is the least significant bit position. B7 is the most significant bit position for an 8-bit value. Further examples are mask.B3 and port B.B7. Mask is a variable name that would have been declared by the programmer. The second way in which we can address bits is to use the name of the bit with the suffix underscore bit. For example, RB3 underscore bit and RP0 underscore bit. Let's look at some examples where we are assigning some values to some individual bits in file registers. In the first example, we are setting the global interrupt enable bit. In the second example, we are clearing bit 7 in the file register PIR1. In the third example, we are setting bit 3 in the GPR identified by the variable mask. In the fourth example, we are clearing pin 3 on port B. Port B is also known as RB. The number that follows the letters RB refers to the bit position and hence the pin position. So in this example, RB3 means pin 3 on port B. In the last example, we are setting the register bank select bit 0. In this illustration, we want to show the structure of a code that can be used to provide two alternate actions depending on the state of a bit. The bit in question in this illustration is pin 2 on port A. It is referred to as RA2. We make use of the if-else statement to provide two alternate actions that can be performed depending on whether bit RA2 is cleared or set. There are situations where it may be necessary to insert assembly instructions in a Mikro C program. The keyword ASM is used for this purpose. To insert a block of assembly language instructions, the instructions are placed in a pair of braces and written after the keyword ASM as shown in the first illustration. To insert a single instruction, the instruction is written after the keyword ASM as shown in the second illustration. From the beginning of this lecture, we have been looking at the features of the Mikro C programming language. Now let's go into Mikro C programs. You probably may have already noticed that whenever we start learning programming, we use the Hello World program. In the programming of PICs, the Hello World program is the flasher program. Some texts may call it the blinker program. This is a program that flashes port pins, usually at a rate of 1 flash per second. The idea behind the program is to first set all the port pins high, then delay for some time. In the illustration shown on the flowchart, the delay period is 1 second. After the delay, the port pins are set low, and then another delay of 1 second is executed. After this delay, the port pins are set high. So this process is repeated continuously, and the result is flashing port pins. That's the program that performs the flashing function. All the program statements are written in the main function. We begin by configuring all the port pins as output pins. This is done by writing values 00H to the trace registers. The continuous flashing of the port pins is achieved by means of a do-while loop. Inside this loop, we begin by setting all the port pins low, then execute a delay function. After that, set the pins high and execute another delay function. The while one is used to ensure that the loop executes continuously and endless. The delay can be achieved in software. The basic idea is to increment some variable from one value to another in a loop. In our illustration, we are incrementing the variable I from 0 to 255 in a for loop. Each increment of the variable takes some time. By the time the variable reaches 255, a time delay period would have been achieved. When using a single variable, the time delay period may be too short to meet our requirements. Therefore, to increase the time delay period, we use nested delay loops. In the illustration, we have introduced another loop, which we can say is an outer loop. This loop is in this loop, we are incrementing the variable j from 0 to 255. For each increment of the variable j, the variable I would have increased from 0 to 255. Therefore, the outer loop has an effect of multiplying the delay provided by the inner loop. At the end, we are going to have longer delay periods. That's the complete program now with the delay function added. Now we go into an exercise. In this exercise, you'll be required to attempt all questions from chapter 3 tutorial questions. After that, you'll be required to submit responses to the questions indicated on the slide via the Google Classroom platform.